Welcome back. This is the first installment in the two-video series on energy profile. Now, what's the purpose of the video, you may ask, and that is how conformation of a molecule can influence its stability. Now, if you notice right here, I've underlined the word conformation. Now, you may be wondering, why did I do that? The simple reason being, as we begin to explore the idea of energy in the context of a molecule's stability, you notice we'll be using Newman projections. And the very first thought that runs through your mind is, oh, he didn't have a chiral carbon, he didn't have R and S, he didn't show us whether there's front or back. That's because R and S leads to configurations, not conformation. Conformation is how, when we learn, you're given them a formula and you write multiple structures, each of them turned out to be an isomer. So those are called conformation. R and S configuration is analyzing the molecule in the internal viewpoint, and that's different. So whether a molecule has R or S, whether it's chiral carbon or not, none of that matters. Every molecule has its own stability level, and that's influenced by how much energy is stored in it. If more energy is stored, that is, higher the energy stored, the molecule as a whole is less stable, and lesser the energy stored, more stable the molecule it is. Which brings us to the second purpose, and that is, actually purpose 2 is sort of related to purpose 1, except we added the element of energy. Generally, as I said, a molecule with a very low potential energy stored in it is more stable, and higher the potential energy stored in it, the lesser the stable it is. And we're going to learn how the conformation in itself is influencing this relationship. Now, before we get going, I do want to warn you again that just forget about R and S, okay? R and S has nothing to do with the energy of a molecule. Okay, R and S simply has to do with optical rotation, that when it is thrown in a polarimeter, whether the light is thrown in the clockwise direction or counterclockwise direction, can tell you something about the purity, if that's what you're interested. R and S has nothing to do with energy. Okay, let me quickly throw these all on the screen so I'm not wasting time bringing one at a time. Now, there's two primary domains of conformation. One is staggered and the other is eclipsed. Now, staggered is two variants, staggered anti and staggered gauche. Eclipsed is just eclipsed regular, which is eclipsed, and eclipsed syn. Now, in chemistry, syn, not to be confused with the word syn as in S-I-N, this is S-Y-N, which leads to items being on the same side, and anti means items being on the opposite side. Okay, I don't want to go further at all, but all I can tell you is, generally speaking, staggered conformations are more stable than the eclipsed variants, and within the staggered anti is the most stable, followed by staggered gauche. And within the staggered gauche, it could be multiple variants, which we will see, and then we have the eclipsed and eclipsed syn. But if you're just looking for the most extreme, then the eclipsed syn is the least stable, and staggered anti is the most stable. Because think about it, my own class, because I give you more freedom to do things in your own speed, I give you varying amount of time, means you're further apart in terms of how far you want to learn, you do better. Put everybody in one big lecture, thrown in a ton of material in one go, it's too packed to be successful, so you don't understand as much. Same thing. Syn as in put everybody too close, anti as in put everybody further apart. Okay, so as we begin to do the rotations, we would have a Newman structure. And if you remember our Newman projections, there's the front and the back. We would move the back portion of the molecule 60 degrees each time. So the rotation is carried out by 60 degrees. Imagine this, a circle, okay? I'm just showing a circle. This has got nothing to do with Newman. So if assuming we start here, okay? We rotate 60 degrees, I'm gonna be doing all my rotations counterclockwise, so I suggest you stay with that. You can also do clockwise, will be the same, it makes no difference eventually. So you'll have 5 variants and 2 identical structures. You'll see all that in just a second. Again, you rotate 60 more degrees. And go ahead and do a decent job. This is another 60 degrees. So you end up, first you ended up here, second you ended up here. We keep going, 60 degrees more. Eventually you'll end up back where you started. So the first and the 360th degree molecule are identical, but then we have other variants that we will look at, and we classify them as whether staggered anti, staggered gauche, eclipse, syn, or within staggered gauche we will have different variants. Okay, different variants within the eclipse as well. Okay, so this is a molecule, it's butane. So the asterisk indicates the 2 carbons around which I have drawn the Newman projection. So we got the CH3, the carbon, one of the asterisk carbon contains 2 hydrogens and the other contains 2 hydrogens. Now this is what I meant by, to draw Newman, it doesn't have to have front and back, at least for the energy and stability perspective. So let's actually go and do this in action. Okay, I've already pointed this out when I explained generally lower the overall energy of a particular conformation, the more stable that conformation or the molecule is. Okay, so we're going to plot energy versus angle of rotation starting from 0 and then 60, 120, 180, 240, 300, 360, and draw a graph. Okay, but for that, let's put the actual Newman. This is fully eclipsed, right? If you notice, this is a CH3, this is a CH3, right? So this is 0 degrees. Say we're starting at, this is 0 degree. We haven't moved anything anywhere. Now I'm going to rotate the steering wheel of the back portion of the molecule by 60 degrees. Okay? I'm rotating 60 degrees counterclockwise. Just the back portion, the front stays the same. It's not going anywhere. What did you see? The methyl group has moved 60 degrees. The hydrogen has moved 60 degrees. And the other hydrogen has moved 60 degrees as well. Basically, you just keep moving. Okay? So this is after a 60-degree rotation. Okay? This is fully eclipsed. If you notice, in the whole molecule, the CH3 is the biggest group, right? Single most biggest group. It's like a monolithic rock. This is the single most biggest group. There's 2 CH3s right next to each other. Okay? And as I said, eclipsed and eclipsed syn is the least stable. That means 2 big groups are on the same side and they're right next to each other. So this is an eclipsed syn. You can only have one eclipsed syn in the entire molecule. Okay? Syn refers to 2 identical or 2 big groups. It could be another big group as well, but 2 big groups are right next to each other. So this is eclipsed syn. So this is the least stable right away. How do I know? Because I've already done this before. But if you're going to do it, you have to go the whole sequence. Okay. Now, when it's not eclipsed, eclipsed always means 2 things are right next to each other. Whether they're big or small, this is eclipsed. If it's not eclipsed, it's staggered. So this is staggered. Okay. Staggered. Now, staggered anti means the 2 big groups are opposite to each other. That's the only condition where it can be a staggered anti. The 2 methyl groups, this is not eclipsed, this is staggered because it's not overlapping. But is it staggered anti or staggered gauche? If 2 big groups, okay, are within a 60-degree distance, that's called a gauche. If two big groups are 180 degrees apart, that is exactly opposite. That's a staggered anti. So this one has only two big group interaction 60 degrees apart. So this is staggered, just staggered. Let's call it number one. Actually, I'm going to call this number one. This is number two. Okay, east in. Let's do another 60-degree rotation, and we get this. Again, we're back to another eclipse conformation, except this time we have a methyl and a hydrogen, a methyl and a hydrogen. At this point, you really can't tell right away whether it is more stable. Of course, it is relative, but we know it's not going to be as least stable as the east sin, but that means you got to keep going. Okay, one more time. Again, we're only moving the back. Okay, we move the hydrogen again 60 degrees more. Now this is one methyl, this is the other methyl. These are exactly the opposite, right? Furthest away. When the two big groups in a molecule are the furthest away from possible, that is called a staggered anti. Means that is the most stable. So this is eclipsed as well. I'm just going to say E, and this is number 3 structure. This is number 4. You can only have one staggered anti and one eclipsed sin. Okay, let's do another 60-degree rotation, and we end up with this. Again, we ended up with an eclipsed number 4. We still can't determine place where these eclipsed are relative to each other until we actually get to 360. We can sort of, but I'd rather wait. Let's do another 60. We end up at another staggered conformation. Okay, this is another staggered, right? This time there's only, again, still only one big interaction 60 degrees apart, which is similar to this, right? There's basically no difference between this and this. However, there will be a different gauge on the next example, but there's only one gauge interaction. That is, two big groups are 60 degrees apart. This is staggered number 5. Okay, let's do another 60 degrees. We ended up where we started. So this is number 6. This is eclipsed sin as well. So we don't need both, but we need that for reference. So this is 60, this is 120, this is 180, this is 240, this is 300, and 360 degrees. So as I said, eclipsed sin is the least stable. That means it has the most energy. So let's say if this is 0 degrees, okay, that means we're starting at the highest energy possible. So this is corresponding to molecule number 1. And as I said, generally eclipsed is less stable than staggered. So staggered 2 and staggered 5 are containing only one gauge interactions, that is 60 degrees apart between the two biggest groups. Since they're exactly this, there's only one interaction in each, and it's actually only 60 degrees apart. Okay, staggered 2 and staggered 5 should be at the same energy level. Now this is arbitrary, okay? I'm not giving any specific values. So this is number 2, okay? Don't get carried away, just leave for 2 now. Let's go to 3. Eclipsed, right? Now this is fully eclipsed in, is the least stable. So 3 and 4 are sort of the same thing, right? You got one methyl to hydrogen, two hydrogens to hydrogen and a methyl, right? It's exactly the same. So 3 is sort of below number 1, but not higher than number 1. So this is number 3. And then we come down to the staggered anti, which is the most stable. So it should definitely have lesser energy than number 2. So this is number 4. And then you go to number 5. Number 3 and 5 are almost exactly identical. So they should be at the same level. And then, right? Sorry, this is 2, 3, 4, and then 5 is same as, right? 5 is same as 3, and then we have gauge again, right? Staggered gauge, which is sort of below 2, but not above, not below 4. Okay, so it's in between these two. So you don't have to be, I should have drawn 4 a little more or less, but you know, you see it's below 2, but slightly above number 4, right? So 1, 2, 3, 4. Oh, I wrote this as 5, sorry. It should be 5. That's why I was wondering, the numbers don't tally. Number 7. So this is number 6, because staggered is still, because the interactions are the same, it should be at the same level as number 2, right? Number 2 and 6 should be at the same level because they're the same Gauss interactions. And then number 7 is same as eclipse sin. So I'm not going to extend it. I'm just going to leave it saying it's at the same level as number 7 should have the same energy as number 1. Number 5 and number 6 and 2 should be the same. Think about it. It's only one Gauss interaction and it's only on the left or right side, but that's not going to change. And number 3 and number 5 should be the same. And number 4 is an odd one. So this is the lowest. This is the highest. That means structures 1 and 7 are the least stable. Well, 7 is exactly the same as 1. So 1 is the least stable and 4 is the most stable structure. Okay. Now let me just stop here for a second and just take a second to walk through the Gauss. Okay. Gauss is still part of the staggered family. If it's not eclipsed, it has to be staggered. Okay. Staggered means things are what? Spread apart. Eclipse means they are right next to each other. Now, staggered Gauss is only referring to the two big groups. If they are 60 degrees apart, that is Gauss. That's what it means. Now, if you have only one Gauss on its counterpart, then they have the same energy. Let's say if one has two Gauss interactions, but the other has only one, then the one with more Gauss interaction is relatively less stable compared to the one with only one Gauss interactions. And there can only be one staggered anti and one eclipsed sin. Okay, I suggest you go through the video and watch it again. I'm going to stop this here and come back with the second example, which is slightly more complex than this one. All right. If you watch this video one more time, you're going to understand everything I just said. It may sound a little bit odd the first time around, but I promise the second time it's going to make more sense. Okay. So this is all as energy profile. This would definitely be on a professional exam if you sit for one. All right. So stay tuned.